We now analyze some algorithms, some basic algorithms in the AI model, just to see how it can be done. So I have 3 examples here, so all of them involve numbers. So assume that I have an input of n numbers, capital N numbers, in blocks of size b. So assume this is my disk that stores these capital N numbers. Every b numbers are stored in one block, like this over here. Okay. So the total number of blocks will be small n, which is equal to capital N divided by b. And given this input on the disk, I want to solve the following problem. So the first problem is quite easy, is to find the maximum number among these input numbers. If you just think about it for a second, you will realize that it's not too hard to solve it, and actually the solution is very similar to the classical solution that we have. So basically initialize some variable that's going to store the maximum, and then just in a for loop read the blocks one by one. So in the first iteration of the loop, we read this block into the memory, and then we go through all the elements of this block and then update the maximum. Then we go through the next element in the memory, next block into the memory, and so on. The important observation here is that once we have looped through the elements of a block, we don't really care about that block anymore, so we can just toss it away from the memory. This means that the memory can only needs to store one block. It just needs to have space for one block. So if the memory size is bigger than b, then I can easily implement this algorithm because I can just keep one block into memory, and then I can go through the elements of that block. So with that assumption, how can we analyze this? Remember that in the AI model, the complexity that we're trying to analyze is the total number of block reads and block writes. In this algorithm, I don't need to write any blocks because I just need to find one value. But I need to read the input. And I can read every block exactly once, because once I'm done with the block, I don't need to read it ever again. So the analysis of this algorithm is quite easy. I have exactly n block reads, so therefore the AI complexity, which is the total number of block reads plus the block writes, is n, which is O of n, so therefore this is essentially what's called linear complexity. Now let's look at the second problem. This is a little bit more complicated. It is the partition problem with a pivot. Okay, so now we're given a value p, and we want to partition this input into 2 parts. So in other words, after this algorithm, the disk should change. So the disk should have essentially 2 sets of blocks, like this and like this. And all the elements in these blocks should be smaller than p, and all the elements in these other blocks should be at least p. Okay, so that's how they should the disk should look like. So I will need to change the data, so I will need to do some writes. Okay. If you think about this problem is also not too hard to solve, and in fact it can be solved with one of the classical solutions for the partitioning, which is something like this. So this is one of the classical partitioning algorithms. If you don't remember how this works, is I'm gonna go over this. We initialize 2 variables, I and j. So I is at the left, initialized to 0, and j at the end. Actually, this should be n minus 1. And then what happens here is that you move I to the left, and j should move to the right. Okay. So as long as the element at position I is smaller than p, we're happy. We can increase I by 1. So this while loop terminates at an element at the position I that is bigger than p, or at least p. Okay, so it stops there. So this element is at least p. Similarly, this second for loop will get stuck at an element j, which is smaller than p. Okay. So therefore, I have found an element that is smaller than p on the right, and I found an element that is at least p on the left. So therefore, I could swap them. The only thing I need to check for is that if I and j have swapped places, then I'm actually done with this algorithm. So in other words, if I is at least j, then I have actually finished with the partition. Then I can just swap these places. Okay. So how can I implement this with in the AI model? I want you to think about this and pause this, and actually I'm gonna pause my own video to fix my. Okay, so if you thought about this, then you'll see that it's actually not too complicated. Basically, we just need to be a little bit careful. So, but we need a slightly stronger assumption compared to finding the maximum. So in other words, we need to assume that the memory size is at least 2 times b. In other words, the memory can have at least 2 blocks. Typically, all these assumptions are quite harmless, because we can assume that the memory can at least have a constant factor of, or constant number of blocks in it. That's always a safe assumption. And in practice, the block size typically is order of the kilobytes, maybe at most a megabyte. Whereas obviously nowadays we have much more RAM than that. So the assumption that the memory size is at least some constant factor of the block size is quite reasonable. But assuming that, then I can afford to have 2 blocks into the memory. So therefore I need to have the 2 blocks containing the element AI and the element in J in the memory. Okay, so assume that let's say this element or this block and this block are kept in the memory. But I need to do something more, because I need to do some writes. And the way you can write things is that imagine that I needs to increase and it passes the boundary of a block. Okay, so let me just erase this. So assume that I was here right at the edge of the block. Okay, then I need to run this while loop that increases I by 1. When that happens, when I crosses the block boundary, and I can actually know that with a bunch of if statements over here, what I do is that I write this old block to the disk. So this old block will be written to the disk, and this new block will be read from the disk. Okay. The elements of these old block is kept in the memory by assumption that we keep 2 blocks in the memory, one containing AI and one containing AJ. So these elements of this block are inside the memory, so I can write them to the disk. Once I've finished writing with them, I can now ignore them. I throw them away, and I keep this block into the memory. So therefore my algorithm. And now we're almost done with the analysis of this algorithm. Okay, so basically we need to write every block exactly once, and we need to read every block exactly once. So therefore we have n reads and n writes, so therefore the total complexity is going to be O of n. Oops, I did something wrong. Yes. So now let's look at the final problem, that is quicksort. So you might think that quicksort is probably very tricky to analyze, but actually it's not, because quicksort is just a recursive algorithm that calls partition. So it can be analyzed relatively simply. So here I'm going to make one simplifying assumption, and that is that the pivot that we pick is the median. It's in the middle of the elements. Okay. And if I want to analyze this in terms of the number of blocks, then it's actually quite simple to analyze, because assuming that somebody gives me a pivot in the middle, and actually I'm not going to talk about how it's done, but if you keep an element randomly, if you pick a random element, then you expect the pivot to be in the middle, so therefore this analysis kind of makes sense in the expected case. But ignoring those technical issues, assume that I have a pivot that is in the middle. After I do this partitioning step, I will have half of the blocks, n over 2 blocks, smaller than p, and n over 2 blocks larger than p. Okay, and then I could just recurse on them. So the recursion becomes f of n equals 2 times f of n half plus O of n, and this O of n is because of this partition step. So therefore, if you know Master's theorem, this solves to n log n. But small n is capital N divided by b, so therefore if I do the substitution, my analysis becomes capital N divided by b times log of n divided by b. Note that this is actually quite a bit of improvement compared to the normal sorting, because if you do normal sorting, then you get capital N log capital N. Okay, so the comparison between these two is actually the gap between these two is quite big. So this factor is at least a factor b smaller than this factor, and this factor is also slightly smaller. This means that if your block size, for example, is, I don't know, 4 kilobytes, let's say, so 4 kilobytes, or let's say 4 or 2 to the, let's say 4,000 integers, then you're doing 4,000 fewer block reads compared to, let's say, a naive algorithm. So, and this shows up once you think of an algorithm that is not like this. And now I bring back to heap sort. Because if you want to analyze heap sort, it turns out that the IO complexity is not much smaller than capital N log n. So in other words, heap sort does basically the same number of IOs as it does comparisons. So the running time of heap sort is n log n, and the number of IOs of heap sort is n log n. So every memory read in heap sort should be accompanied by a block read. And now when we compare these two things, we realize that this guy is a factor b larger than this guy. So therefore heap sort has a much worse IO complexity compared to quicksort. And this can explain the gap that we saw between theory and practice, because if I go back to the picture that I had before, this was where we started the story. Heap sort kind of blows up as your input does not fit inside the particular level of cache. It blows up a little bit once it doesn't fit in L2. It blows up a little much more when it doesn't fit in L3. And if this experiment continued for input sizes that don't fit inside the main memory, so therefore need to be stored in the disk, then this will blow up even more like this. Okay, whereas all the other algorithms, especially if the quicksort or merger were implemented in the IO model, they would just maybe moderately increase a little bit. So they're much more sensitive. They're much less sensitive towards this change of model. And that's one way we have managed to explain this discrepancy between theory and practice, by introducing a new model of computation that takes into account different costs of accessing an element. An element that lies inside a main memory has a different time of the access time compared to an element that lies in a cache or an element that lies on the disk. So by just this simple model, this is model number 2, we managed to bridge a gap between theory and practice. Of course, this requires both theoretical justification and experimental justification, right? So experimental justification, for example, is like this. This is experimental justification. And again, if I slide much further ahead, this is a theoretical justification. And this is essentially what we could do in algorithm engineering.